teman-teman Syamakum. So, hope you are doing well. So we meet again in this 10th session of this course, Design and Analysis of Algorithm. And firstly, please do the presents. I sent the code in the chat box. So before I start, I would like to know if my voice is clear to you.
Yes, sir.
Okay, that's good. Because there is no feedback, so I'm afraid that I'm disconnected or maybe there is an error in my network. So okay, today we will continue to study about the design and analysis of algorithm. And previously we have already discussed about complete search, but not in a particular session. Well, we have discussed further about divide and conquer, and discuss about dynamic programming and several test cases. And now this is the fourth. Well, this is the fourth paradigm, which called greedy algorithm, not algorithm, greedy paradigm, or greedy method, or greedy technique. Let me record on this computer. So this is the greedy method, and this is the list of the reference. Mainly, I took the course from competitive programming and pemrograman kompetitif dasar from here, followed by the Corman introduction to algorithms, and for the online resource, I take a lot of resource from Abdul Bari. This is the YouTube channel, the Indian guy, and Geeks for Geeks for the source code, etc. for the reference. And this is the outline. So we will discuss about the definition, then greedy concept, problem categories, and we have 3 case studies today. And then we'll close with the limitation of greedy technique. Okay, we start with this one. What is greedy technique? Or what is greedy? Well, greedy is a technique or problem-solving paradigm, not a specific algorithm. So whenever you encounter or you see there is someone called greedy algorithm, maybe they refer to specific or a category of algorithm that apply greedy paradigm. So not because greedy is not an algorithm. This is a solving paradigm, problem solving paradigm. And this technique usually has a fast execution time, well, because it's local optimal and it's easy to implement. Fortunately, compared to dynamic programming, this one is, well, alternatively easier to imagine or to implement. But sometimes it's difficult to prove the truth. Well, this one is the opposite. On the other hand, when we use greedy, it's like we use, trivial or with several cases, we have to prove it with several cases or with counter example, etc. And this is difficult because there is no exact whether this is for the proving. It's a little bit difficult. Even in mathematics, we applied like a trivial approach. And in this one, this is the important keyword. When we studied about dynamic programming, you remember that we have to define the state problem state. Sorry, we have to define the problem state and the problem transition. So there are 2 keywords in dynamic programming, and of course, memoization. And in this one, actually, it's only one, which is greedy choice. It will how good you choose the choice, the greedy choice will determine your accuracy of your correct answer. So what is greedy choice? Greedy choice allows to choose the decision that is guaranteed to produce an optimal solution at that time, or well, for another term we call this as local optima, local optima, without considering future factors. So we only consider the current state and what's the local optimal for current state. That's one we choose. Then this gives the impression of being greedy. What does it mean? So this is the reason why it's called greedy. It is only concerned with the problem at hand and always making the best decision at the time. So whenever we saw the current state or the current resource, we take the most efficient or the most optimal as possible. So when we see another option or another resource or another solution, then we increase our understanding for finding the local optimal. That's how how greedies work. Then that's the definition. Furthermore, this is for the concept, the characteristic of problems that can be solved using greedy technique. So actually, it's a little bit it's a little bit similar with dynamic programming, and maybe you think sometimes you don't realize it when you solve the problem. Maybe you just thinking, I use brute force, I use complete search, backtrack, etc. But actually, you apply greedy approach. So the optimal solution of the problem can be determined from optimal solution of the sub problem. So with greedy technique, it's similar to divide and conquer. Well, the term we can use the similar like divide and conquer and dynamic programming, where which is used which split the problem into smaller sub problem. For each sub problem, there is a step that can be taken to produce an optimal solution for the sub problem, and this step is called greedy choice. So at current time or at that time for the sub problem, we have to choose the local optimal solution. It's a little bit different when we choose like for dynamic. Maybe for the sub problem, it's not the local optimal. Well, it's not the local optimal, but it will generate the global optimal. It takes a lot of practice to build well. This is it's normal. It takes a lot of practice to build intuition and experience to master the greedy technique. And actually, it's a little bit difficult and it's a little bit risky if you apply this technique for the competitive programming, because you couldn't prove it firstly, and you can't prove it correctly or rapidly, and then it takes it's risky whether the answer is in general the answer is normally, if not accepted, it's always in wrong answer, not TLE or not TLE or there is runtime error. So actually the answer will be whether accepted or wrong answer. And this is the classical problem categories in greedy. Actually, a lot of categories. But if we consider like the pattern of for several categories, for example, for activity selection, load balance, interval covering, or job scheduling, it's a little bit it's similar. For this one, activity selection, there is an interval, and then we have to select the proper activities, the optimal possible activities. Well, for interval covering, given in an interval, you have to cover the minimum resource. Or for job scheduling, it's similar with the interval covering, something like that. And other things, we have coin chains, which is this is in the classical category in greedy also. In dynamic programming, but in grid there is a specific or special case. So there is a greedy version. I will show you later the differences between a problem with dynamic programming and greedy. And then the fractional knapsack, actually, this is similar with, well, 0-1 knapsack, but for 0-1, we have to take it or we have to leave it. But in the fractional, we can take like half of them or only 75%, etc. So it's right. This is why we call it's called fractional. Other things for load balancing, it's normal, well, general load balancing, and for this two, it's about the graph. Well, for human codes, normally in distribution, in compression, etc. And this two is applied in the graph. Minimum spanning tree for finding the spanning tree, the minimum width of spanning tree, and for a single source shortest path problem. So maybe you are a little bit familiar with Kruskal, Prims, Dijkstra, maybe Voigt-Warsaw, etc. So this is the classical category. This is how we build experience and how we build intuition. But well, this is a little bit tricky. Why? Because the problem generally it's relatively easy or not as difficult as dynamic programming. So, for example, for activity selection, well, there is a pattern, but there is no exact code like when we try with knapsack 0-1 knapsack or coin chains. Give the like our discussion previously. So in this case, it's more like well, small program, and then this is activity selection. Maybe we can apply it, but we have to modify some things. It depends on the problem. Okay, so I will share this presentation, and you can check for the link for the blue underscores. Underline. Sorry, for the blue underline text, there is a link, so you can access it. For example, for fractional, knapsack, half-man code, Dijkstra, Kruskal, Prim, there is the source code also, so you can apply. And we will continue to discuss for each case study. But before we going to discuss case study, this is the important remarks for greedy technique. Important problem solving strategy usually applicable to greedy problem. Actually, when you use a greedy problem, the tips or the trick or the tips is that you have. It's better to sort the input data or to sort the problem. So you can, by doing this, you can optimize your greedy strategies, optimize computation time. Then second one, using greedy algorithm to attack non-classical problem is usually risky, tends to obtain wrong answer verdicts, not TLE, but wrong answer. Well, more like wrong answer. And the third one, proving that certain non-classical. Well, normally when you encounter a problem that's similar with the greedy or dynamic programming, I suggest for you to solve it with dynamic programming. Except if there is a limitation like the size limitation is too big, etc., then you could consider greedy, because greedy is faster than, in general, it's faster than dynamic programming for the execution. Proving that a certain non-classical problem has optimal substructure and greedy property during contest time may be difficult or time-consuming. This is how it's difficult to prove for certain non-classical problem. Well, actually, for classical, I will show you later about the keyword for its problem or for its category. And this is important tips for the competitive programmer warriors. Do not use greedy if the input size is small enough to accommodate the time complexity of either complete search or dynamic programming approach. So if the input size it's small enough, it's less than like 1 billion. Okay, so maybe we can consider dynamic programming or complete search before we apply greedy. Except if the input size given in the problem statement are too large, even for the best complete search or dynamic programming algorithm, then we can consider greedy. So this is like leveling. Try to solve it with dynamic programming. Then if it's not, or whenever you are desperate, solve it with complete search or brute force, and then you optimize it when it gives like time limit exceed or memory limit exceed. You can consider dynamic programming, but if it still give you like a time limit or memory limit, then you can consider greedy. It's quite challenging to come up with new non-classical greedy problems. Therefore, the number of such novel greedy problems used in competitive programming is lower than that of complete search or dynamic programming problems. So that's why actually challenging to come up with new. The idea of problem to solve, well, the idea of the proposed idea for that can be solved with greedy approach, which is non-categorized as non-classical. This is, well, it's a little bit difficult than when we propose it in dynamic programming or complete search. So it's not, it's rarely shown this problem, but it's worth to know because it's important for your daily activities. So, okay, we'll start with this one, case study one, interval covering. So this is the first category that I want to discuss. Actually, the definition or the keyword is simple. Find the minimum number of resources to cover an area in the interval of A and B. Suppose you have let me draw something. You have a line, something like this, maybe road or line, some line, and then you want to cover all of these things. Like you want to open Indomart or Alfamart, then you want to cover the distribution, so you will get the optimal range of customer, and you get the minimum shop that can reduce the number of operational costs. So you can apply something like this. This is like the interval covering. So this is like the shop. You have to, in this case, we can use this one, 1, 2, 3, 4, and 5 shop, instead of maybe putting it randomly or just putting it as nearly, well, in certain range. So this is quite important for you for the daily activities and it's practical for an industrial problem. So this is the interval covering. And we start with this problem. I think it's better to visit this problem. Wait, let me check. Stop share first. Before I continue to the case study, is there any question so far? Maybe you are not clear enough. So if there is no question, so that's good. Thank you, Rosa, for giving the feedback. So, okay, you can visit this one. Let me share this one, gas station. So, download this one. So, G gas stations are authorized to operate over a road of length L. So, it's one dimension. Its gas station is able to sell fuel over a specific area of influence. So it has a area of influence defined as closed interval. This one, this is closed interval, which means the value over here, like for example, it's 10, then 10 is included. So x minus r plus x plus R, where X the station location, or this is the point. Like in Bahasa, we can call in well, in highway we can call it in Bahasa like kilometer sekian sampai kilometer sekian. So this is the location. Where X is the station's location on the road. 0, which is the value 0, less than or greater than X, less than or greater than L. What's L? We'll discuss later. And R is in its radius coverage. L, this one is the length L. The radius of coverage from 1 until L. The point covered by a gas station are those within its radius of coverage. So, like what I show you previously, given a single line, horizontal line, one-dimensional line, and then you have to put there is a location of the gas station, and you have there is diameter or the area of influence, the distance, radius of coverage, this one. Then you have to calculate whether all the line are covered or not. It's clear that the areas of influence may interfere, causing dispute among the corresponding gas station. Maybe there is overlapping cases. So this area of influence is overlapping between the previous gas station and the next gas station. It's possible. It seems to be better to close some station, trying to minimize such interference without reducing the service availability along the route. The owners have agreed to close some gas station in order to avoid as many disputes as possible. So you have been hired to write a program to determine the maximum number of gas stations. Actually, this problem is very practical. Well, for us, we live in Indonesia, which is not, well, mostly if we live in Java, it's not really the problem because we have we have a lot of village or a lot of near city. But if you live in Papua, Sumatra, maybe in the road, Sumatra or in Kalimantan, maybe it's difficult to find the next gas station. So you have to define the correct or exact location for the gas station. Well, maybe it's I don't know. I never go to Kalimantan, so I don't know the real case. But like in the continental countries, like in Europe or in China or in US, normally, or in Australia, normally the road is very long and there is nothing beside. So you have to pay attention. That's why it's important. But if some point of the road is not covered by any gas station, you must acknowledge the situation and inform about it. So this is the input. This is how we read the input. For the first test case, several test cases, the first line of each test case contains two integer numbers, L and G. This is L, which is the length of the road, and this is G, which is the number of gas station. Separated by blank, represent the length of the road and number of gas station. And this is the limit. The length is up to how much? 10. Yeah, 10, not 10, 100 million. And G up to 10,000. Each one of next G lines contains two integer number, X and R. This is X, this is the location. Oh, sorry, this one also. 5, so this location 5, and this is the radius of coverage, radius of influence. So if we have 5, something like, let us draw this one. Given something like this. For example, this is the road. Make it bigger. Okay. So yeah. Maybe this is the coverage. This is the location of the gas station, and this is the radius. So it's possible something like this. Maybe for this one, the area of coverage is longer. And for this one, maybe there is a case where the problem something like this. So there is a gap which is not covered. And this is the overlapping situation. So for example, in the point 5, the radius is 5, which is from this one, from 5 over here until 5, maybe this one until 0, then like really over here until 5 plus 5, which is 10. It's covered by this. This is the area of influence. Then for the next G gas station in the point of 20 with the radius of 10, then followed by 40 with the radius of 10. Sir, what if, as we can see over here, the limit is only 40 and this one limit only 10. So we can do something like this. Imagine that the position is like in the most right or the top left, which is actually it's covered something like this, but we only consider until the optimal position. So it will be like this. Similar also with this one, but actually for the programming code, you can consider like this, and you can limit it to this one. Okay, so that's 5, 10, 20, 10, and 40, 10. I think I will create it in Excel. Try to understand the problem while explaining, maybe while I'm preparing the presentation. So it's like this one. As you can see, imagine that this one is the spot. So 5, it means like over here. 5 is open here, over here, and the area of influence, which is plus 5, which is up to this one, and this one, and of course this one. So 5 to the left and 5 to the right. And for 20, so this is 20. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will be like this. Let me check. And 10 over here. 3, 4, 5, 6, 7, 8, 9, 10. This is one, and the 40 also. One, two, three. So actually it's 10, something. This. Which color is this? Well, I forget the color. So as we can see in here, there is no For each test case, print a line with the maximum number of gas stations that can be eliminated. But in this case, it couldn't be eliminated because it's important. If we eliminate this gas station, it won't be covered, as well as if we delete this one also. So that's why over here it returns the value of 0. So for each test case until the end of this one, then you print, you enter, it will show directly 0, which is there is no gas station that can be eliminated. And then we move to the next test case. So this is the next test case. We have the same 40, and then we have 5. So let us test case 1, test case 2. So 5, 5, so it's similar. I just copy paste this one. And then 11 and 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. And then the third one, there are 20, 10, which is similar to this one. Copy paste this one and change the color. Then what else? Let me cut this. 2010, and we have 33, which is over here. 1, 2, 3. 3. And 40, 10, which is similar to this one. One, 2, 3, 4, 5. Okay, that's all. As we can see over here, 45, we have for 5, we have 5, 5, 11, 8, 20, 10, 33, and 40, 10. If we see over here, actually, we can eliminate several things, several gas stations. For example, this one, we can eliminate it because we have this one and this one, as well as this one also. So that's why the output over here is 2, because there are 2 gas stations that can be eliminated to minimize the operational cost of a gas station, the number of gas stations. And that's all until the end. For example, I think for this one, 43, 10, 10, 18, 10, 25, 10. So something like this, and 18, 10. Like this, and 25, 10. As you can see over here, there is an area that is not covered by the gas station. That's why it will print -1. So, okay. I think it's clear. Is there any question for this assignment? If there is no question, try to solve it. We'll discuss it in 20 minutes. Let me know if you have any, if you want to give your opinion, or you have solved and accepted, let me know. So, is there any challenger who want to share their opinion? Okay, Dewanga. Okay, Dewanga, go ahead.
Sure, sir. This might be not the best opinion, but I think we could check the, well, let's just say it's sequential. When we first input the location and its radius, we check that is, well, no, assume we have an array of the length of the road. Then we start inputting the station and its radius. Then on the second row, on the second input, we inputted the station with its radius. If it's smaller than the first radius, then it's added the number of stations that could be eliminated. Then so on until the last input.
Okay, but as you can see, actually, the input is not in a certain order. Pay attention to that. So, for example, let me share. Well, for that thing, it works as long as I think, well, it's not always working correctly, actually. But you have to pay attention that the order over here, well, over here it's always 10, 10, 10, 18, 25. But it's possible that you may get like 11, 5, 20. And for this case, maybe, or maybe the previous one actually is, the first one can be eliminated. But because it's exists before, then you you just delete the second one, which is normally more optimal. Is that what you mean? So you just you want to check before you add this one, you want to check if there is any, you can delete it, something like this, or
Yes.
yes, yeah. It's where you are approaching in the greedy technique, but that's not the correct thing to choose the greedy choice. So that's why choosing the greedy choice is it's not easy. But that's the greedy technique also. Thank you. Okay, let me put a point for you. Okay, so I get it. So, is there any other challenger, warrior? Okay, Nabil. Okay, never mind. Okay, yes. Hmm. Okay. Yes. Okay. Yes. Okay. Okay. Yes, actually, that's well, nearly correct. Yes, that's correct. Part to solve. But have you tried to code it, Nabil? Okay. Okay. Thank you. Yeah. That's what I did. I prepared the source code in the next slide that applies similar paradigm or similar approach of greedy. So, is there any other opinion? Okay, Puchwananda.
Okay, so I think I want to add some algorithms to Dewangas and Nabil's solution. For the Dewangas solution, Bapak said that if there's like the input is not ordered, the input is not in ascending order.
Yes.
I think that problem might occur also in Nabil's solution. So untuk menghindari itu, jadi mungkin ketika di input itu bisa di sort dulu. Jadi di sortnya berdasarkan tadi x kurang r di sorting dulu seperti itu. Jadi yang mana duluan, sehingga nanti waktu kita menseleksi itu benar-benar sudah dari kiri ke kanan itu sudah tersortir seperti itu.
Exactly. But by doing sorting, what do you mean? Do you prefer sorting? Well, as you can see, there are two sides, which is the left side, the starting point and the end point. And which one do you prefer? Do you prefer to sort in the left, in the starting point, or based on the end point?
Okay, so I think based on Nabil's algorithm or Nabil's logic, it would be better to sort it with the left or the first number. So sort it by the left point.
Okay, thank you. That's good. Yeah, that's what I did. Okay.
Thank you, sir.
You're welcome. So that's the tips. Well, actually, it's important in greedy. Before you do anything else, just once you get all the input, sort it. Okay, that's good. Is there any other opinion or recommendation or advice? No? So is there anyone have tried to submit the code, maybe? Even if it's wrong answer or TLE or etc. No? Okay, if there is no further answer, then share the screen. Well, then it's combination of Dewanga and then improved by Nabil, and then last minute improved by Putuananda. Yes, this is the answer. Actually, this is the source code. That's why over here I use C++. Well, usually I use C, original C, and but in this case I use C++ because I want to use sort over here, and of course this one is easier to implement. It's practical. So I want to use this one, the standard library, STL. Sort to sort the pair based on the lower bound, so based on the left. Once we got all the inputs, so we sort it based on the left order first. So this is very important. Okay, what I'm doing is over here, while LG and while true, this is so basically it's infinite loop. for all test case, because it will be break or it will be stopped once the value of L over here it's written L and G 0 and 0, but actually if the L is 0, which is the length is 0, so so I just consider only L, the length interval is 0, it means that it stopped. Then if L is equal to 0, break. Then we save, not we don't save we don't create an array of the length of the X and of the L, because it will be it will be wasting of memory. As you can see, the limit is 10 power by 8, so 100 millions. Imagine you create an array with the size of 100 million, and it consists of integer or maybe boolean, but it's large. So we only consider the pair for this one, integer over here. XR over here, actually I save this is, what is XR over here? This is, I want to save this one. So this is the lower bound and this is the upper bound. Like the starting point, the end point. And the length of G, well, by default you can define it. By default, maybe you want to define it 10,000. It's fine. It's not big, too big. But in this case, I want to make it precise. And then take all the input, and then make pair over here. So I save the pair. As you can see over here, x minus r, x plus r. So there is a possibility that value over here is minus less than 0 and greater than L. So it's possible, but it's never mind. I just want to save it first. Once I got it, so I sort it. So that's why you can apply the Nabil approach once we sort it. Don't forget to use a standard library. And then we define the left, right. So we define the left, right, and for the stopping point or checking point. Well, the left never or less than L. So it means that it's not all area is covered in the interval. And then we move to this one. If I less than G, which means that there are still several gas stations that can be computed. And this one, this is important. This is what, based on the Nabil's idea. XR I dot first. So in the first one, we compare less than the left, the current left, less than or equal. So it means that the left is 0. So actually we start whatever in the value, whether this is a minus, we start with 0. So we start from beginning, right? Max right. XR I plus plus second. So what did I do over here? For example, this one. So we start with this one. We start with this one, and then we go. We take the right max, and then we go up again. But in this case, the first is different. It's not less than or equal left. So I think it's easier. But I think it's easier something like this. Can you see this code? Wait, sorry. As you can see over here, so the left is 0, starting point 0, 0, initial point. So we put over here, oh, okay, this one is less than or equal to 0. So we go to here. Then we define the right, the initial value of right is 0. Then we define the right, the new right, which is this one. Then this one, maximum between right between 0 and this one. Second, as you can see, it's first and then second, the upper bound. So the new right is over here. And then we check it again. XR plus plus, I plus plus. So I plus plus is over here, which is more than 0. It's less than or equal than 0. No, actually this is 3. Then it's break or get off from this while. Then if right equal to left break, it means that it reached the final. If not, then the new left is right. So we define this one as the new left. So starting from here, we can visit all possible area over here. So that's why it's yes, it is the same idea as Nabil. And minus minus, this is to remove the selected gas station. So once we select, actually, well, this is the difference. It depends on the problem. Actually, if the problem is asked to print out the number of gas station, then you can use this one starting from 0 and then plus plus and plus plus. But in this case, the question is a little bit tricky. It asks the number of stations that has to be eliminated. So that's why we have to consider this n minus minus. So we eliminate this one because it's used. And at the end, it will keep all the possible, all the not eliminated. Well, it will keep the eliminated station. Sorry. So starting from here, we check the area previously or equal to this point. Where do we check it? We check it over here. So we check it first less than left. Oh, okay, less than left. Then right, we define the new right, maximum right is over here. And then we go to the next looping iteration, which is still comply over here. Okay, less than or equal. So first is equal to left. And then we define right, new right is over here. So this is the new right because it's bigger than this one, the maximum. Then we check it again, there is no more. Then pick out to the looping. And then do the similar thing, we define this one and then we check it again over here. As you can see over here, we delete minus minus. Actually, we delete this one, but we keep this this limit. And then starting from here, we check it again over here. As we can see, so we check over here, it's eligible, and check it again over here. So that's why at the end, it will be minus minus 3. So if there are 5, minus 3, minus 1 3 times, so which is it left 2. So that's how we print the answer. In the case where left is less than L, it means something like this. So the new left is the new left is right, the last right. As you can see over here, it's less than L, so it's we print out minus 1. Okay, what happens if there is, for example, something like this? What happens if there is something like this? Like for this one is test case 4. Actually, if something happens like this, it will be checked over here, right? So we check over here and we couldn't find less than the new, well, we couldn't find the new right, which is the right will stay same as the left. So that's why if right equal to left, then break. So we get out from this looping and then print, we check it. So the left is this one and the limit the L is this one, so it's basically less than. And then that's why we print -1. Is it clear for you to understand? Or do you have any question? It's accepted. Okay. If it's clear for you, then this is how the interval covering is done. So we move to the next problem. Well, for the next case study, I will focus on the the general idea. Just for the interval covering, I would like to ask you interactive. So second case study, second category is minimum spanning tree. And for understanding minimum spanning tree, we have to understand spanning tree. A spanning tree that connected an undirected graph is a subgraph that is a tree and connects all the vertices together. I'll show you later in the representation. A single graph can have many different spanning tree. So actually, given a tree something like this, well, given a graph something like this, you have to convert it into spanning tree. Then if you convert to the spanning tree, the requirement is there is no cyclic graph something like this. So there is no cyclic, and there is no cyclic over here, there is no cyclic over here, there is no cyclic over here. So that's why you have to convert it into a tree. This one converted into tree. That's what we call spanning tree. And a single graph can have many different spanning tree. For example, based on this this graph, you can build several different spanning tree. But the question is, there is a weight for each edge, a minimum spanning tree or minimum weight spanning tree for a weighted, connected, undirected. As you can see over here, it has to be connected. So because it's not connected, it will create at most different two or more, depends on the number of disconnected graph. So this is the connected graph. Disconnected, it means there is another vertex over here, another vertex subgraph over here, but it's not connected directly over with this graph. So the requirement actually it's connected and undirected. Undirected is there is no arrow, which means that it's only we can go to there, but we couldn't we can go from A to B, but we couldn't go from B to A. That's the directed data structure. So weighted, connected, undirected graph is a spanning tree with a weight less than or equal to the weight of every other spanning tree. It means that you can generate several spanning tree with this graph, but for finding the optimal minimum spanning tree, it's difficult. It's a challenging task. So that's why we have to calculate it, and we have to consider several algorithms. And for the application, it's widely used in network design. As you can see, if you, I don't know, do you get or do you take the course of jaringan computer network? Have you taken it?
Not yet, sir. I think it's the next semester.
Okay, I see. The fifth semester. So actually, it's important for building the map or the tree of the RG45 for internet connection or internet cable. Yeah, there's a bus, tree, spiral, etc., circle, etc. So it's widely useful. It's very useful for this network design, computer network, or finding road. For example, you want to visit or you want to distribute all to all the city over here, but you want to obtain the minimum cost or minimum, the minimum cost as possible. So that's this minimum spanning tree on charts, telephone, electrical, etc. So that's why it's important. For the mathematical symbol, it's standard. Whenever you discuss about graph in general, it's symbolized as notated as a G, noted as G, and then you have a set of V and a set of edge. This is vertex, and this edge, vertex. And for vertex, based on this graph, we have A, B, C, D, and E. And for the edge, we have AB, because it's connected, and AE, it's connected, BC, it's connected, BD, etc. And what is spanning tree? Spanning tree is the subset of this one, of the graph, because it's 3, so this is the subset. Why it's not equal to G? Because we cover all the vertex. Yes, this is the differences. For the vertex, it has to be the same as the original graph. But for the edge, it has to be different, at least -1. So that's why over here we don't define we don't decide A, B, etc. But we calculate the absolute value. The absolute value of this set is the number of vertex -1. So this is how we represent spanning tree, which is a member of a subset of graph G, something like this. Then how we solve it? We can use Kruskal, or in this case, we can use, Kruskal or prims. I don't share the source code because you could, I provide the link to the source code. And well, for this one, Kruskal and prim, you can Googling it online. There are abundant source code for the Kruskal and prims. So the differences between Kruskal and prims is, for Kruskal, it starts from the smallest weight. So it saves all the input firstly, and then start from the smallest weight. But in prims, it doesn't necessary to save all the information. Well, it can be start from a random point or random vertex. For example, let's say it starts from A for prims. A, it will choose, as you can see, the greedy approach is over here. This is the greedy approach. Given the current state or current local optimal, given the choice of 3 and 4, which one is would you like to choose? So in this case, we would like to minimize. Then 3 is less than 4, select 3. But in Kruskal, we don't start by the vertex, we start by the edge. So the smallest height of the edge, we have to take it just to make sure that we don't miss it. So for the next iteration maybe. So we select the smallest weight, which is 2 over here. Then for the next iteration, because it's 2, what next? For Kruskal, it will search for smallest, other smallest. Then 2, okay, we plus 1, we move to the next higher weight, which is 3. Oh, there is a 3 over here, so we select it. And in this one, we start with B. So actually, we start with 3 and E, B, C, and D. So we compare 3 of them. So we got 2 as the minimum. So we select C. And this is the next step. So we couldn't find, after that, in Kruskal, we couldn't find the smallest less than or equal than 3. Then we move to the next step, which is 4, 3 plus 1. So we can find 4 over here. There are 2 4. So in this case, you just need to select one of them. Maybe this one is the left one, or this one is the right one. In this case, I select this one. It's up to you. Actually, you can choose this one also. It depends on how you build your program. In this one, we compare C, as you can see, to access there is certain ways to access D, which is using 4 or 5, or using E, there is 4 and 5. Well, you can choose this one also actually, but in this case, because for my current state is over here, I prefer to choose this one, 4. Then the last one, we choose this one, 4. And then we choose how we can access, as you can see over here, we can access E with 5, 6, or 4. Then we choose 4. And that's how you create a spanning tree, a minimum spanning tree. Well, because this is the simple sample example, so it gives the same result. But if imagine you have like more than 10 or more than 20 vertex, and then you have more than 50 edge, so maybe the answer will be different, but based on the approach. Okay, that's how we solve it, the minimum spanning tree. Is there any question? If there is no question, so we move to the next one, which is activity selection, the third case study. So for activity selection, it's like your course schedules. Like you have 24 credits SKS that you can optimize during a week. Maybe you want to graduate early. Then in this case, you have to choose which course it's not overlapping between each other. Then and then you can choose, oh, I can take this course, and this course. So I can optimize it at the end of the semester. you can obtain the most the maximum activity, the maximum course you can select. Okay. So that's the idea of the activity selection. Well, for the interval covering, the idea is to find the minimum. For minimum spanning tree, finding the minimum, but in activity selection, normally it's used to find the optimal, the maximum. Given an activities with the ith activity is expressed in its start and its end. This means that this activity starts in this value, and ends in this value. At the time, you can only participate in one activity. So, for example, you have a choice to take a design analysis algorithm, or you have to take computer network course. And computer network course start at 2 p.m. until 6 p.m. And for the design analysis algorithm, it starts at 1 p.m. until 3 p.m. It's not possible. You have to choose one. You can participate in two activities, I and G, if this one, AI dot n, is less than or equal AG dot start. So it's the same time. For example, you have course computer network. The course of computer network, it starts at 3 p.m. and this course, design analysis algorithm, it ends at 3 p.m. So you can go directly to the next course. You want to set your schedule so that you can keep up with as many activities as possible. And this is the example. Given the example, something like this, for example, this is 1, 2, 3, 4, 5. Oh, sorry. Oh, sorry, it starts at 0. 0, 1, 2, 3, 4, etc. Oh, no, sorry. It's not the same representation. So imagine you have the schedule. The optimal activity that you can choose is this one, the second one, and then the third one. So given 4 courses, for example, you can only select 3 courses. And how we define subproblem? Actually, the subproblem is not this one. A subproblem is the rest of this one. Make sure that the problem can be broken down into smaller subproblems. This is the keyword of activity selection and keyword in general for greedy. And of course for dynamic programming also. And divide and conquer. Assume the first activity you participate is in is activity X, this one. The next selected activity must have an initial time list the greater than or equal than EX. And so as you can see, it's EX is less than or equal than EY, for example, or EX plus 1. If G is the smallest value that satisfies a G start one, for example, this one is G, then we can define subproblem with activities from G to N. From G to N. So this is the subproblem. Not only one of this, but this one. And this is how we choose greedy choice in activity selection. Actually, it's the contrary. Well, it's contrary of interval covering. Greedy techniques don't guarantee solution to problem that have subproblems. Okay, yes. Define the greedy choice. Yes, absolutely. Defining the greedy choice in activity selection. In this case, we have, we have 3 choices. The first one is an activity with earliest start time. Second, it means that we consider starting from the earliest, this one, starting point. And then we select an activity with the shortest duration with this one. So we select the smallest duration, and then we move to the next smallest duration, etc. And select an activity, or this one, select an activity with the earliest end time. So in this case, we consider the end time of the right top, the right most in this one, right order. So the first option is choose the first one, the earliest point, and the third one is just the end point. And not all of these options are optimal. Why? Suppose you have an example like this. So which one is the best, or is better for this case? 1, 2, or 3? So which one is better between these 3? You can open mic, and or you can write it in chat box. Oh. So because there is no, or maybe you want to share why this one is the greedy choice. So actually, this is what I call that for activity selection is the inverse of interval covering. As we can see previously, for interval covering, we have to sort it something like this. We have to sort it. Then we consider from starting point. But in this case, the most the optimal way to choose the greedy choice is to consider the earliest end time. As you can see, based on this example, if we choose this one, we only select one activity. If we choose the shortest duration, we only select this one activity. But if we choose earliest end time, we may select 2 activities. It's easy, right? So this is the case study. Suppose you have 1, 7, 2, 6, etc. It starts at 1. Disclaimer. 1, 2, 3, 4, 5, 6, 7. So 1 to 7, 2 to 6, 5 to 7, 6 to 9. This one 9, 6 to 9. Actually, this one 9 to 12. Wait. Oh, sorry. 6 to 9. Then 9 to 12. Okay, 9 to 12, and sorry, it's not in order. Then this one 10 and 12. This one 11 and 15, and this one 13 and 14. So we start from beginning, but we start with earliest end time. While options are available, so we choose interval 2, 6 because it has earliest finish time. So we visit this one until we found, oh, this one is the earliest finish time. So we select this one. So this one is selected, and this one is the subproblem. And we can delete these two. Subproblem with available option. So the available options becomes 6, 9, 9, 11, 9, 12, 10, 12, etc. Next to the third step, select interval 6, 9 because it has earliest time, finish time. Okay. Then we cut it again. The new subproblem will be like this one. And then in the fifth step, select interval 9 and 12. This one, 9 and 12, because it has the earliest finish time. Actually, it has, sorry, actually it has the same earlier finish time with the 10, 12, but pay attention with this one. If we choose 10, 12, we couldn't satisfy this one. Or actually, is there a problem? No, it's fine because it's activity selection, not the interval covering, so it's fine. Even you can choose, it depends on you whether you want to choose 10, 12 or 9, 12. And then we delete the remaining option. Then this one, there is no other choice, so this is the optimal. 1, 2, 3, 4. This is activity selection, and this is how we create the source code. Sort by end time. C3. So it's like the reverse of interval covering. Is there any question for this activity selection explanation? If there is no question, then I have a question for you. Well, of course, we have. No, there is no question. So I hope it's clear for you. So for the assignment for this week is this one. Create a summary and present it. Pay attention not in TikTok, but in YouTube and listen. It depends. Well, it depends on the content. If you create your content by your own content, so you can publish it. May be useful for you for the for the other programmers, maybe for other students. But if it contains from other part, so keep it unlisted. So the summary, create a summary. This one, choose. You have to choose group of 3 warriors. Well, at most 3. So you can, maybe you want to work by yourself. It's fine, as long as you solve this one, this 3 question. Group of 3 warriors or less. And create 3 video for it's this one. The maximum duration is 5 minutes, so it's simple, right? The one of the common ways is to use Zoom and record it and then upload it. That's all, 5 minutes, which consists of definition at least, which consists of minimum definition, 1 sample problem, and one solution, how we solve it with this problem. And this is the problem or the categories that you have to review in your video: load balancing, single source paths problem, and Huffman codes. Okay. Is there any question for the assignment? This is for until next week. Yes, Dewangga, you want to say something?
So, do we make the video or do we watch the video?
Make the video.
Only. Then the three warriors. How about the three warriors?
Sorry, this one. Sorry. Group of students. So I think it's clear. So it's clear for you and for others maybe.
So we make a group to make 3 video, 1 each.
Yes.
Okay, now I understand.
Okay, is there any other question? If no, well, maybe you can start right now. Actually, I have I would like to ask you previously. I would like to ask you to solve one competitive programming problem, but I think I will save it for next week. So next week we will discuss several case studies of greedy and how we solve it. Okay. So this week is for the theoretical foundation. So if there is no question, then good luck. You can start right now. Can stop it here. Stop the recording. Thank you very much for your attention. Tetap dijaga kesehatannya. Selamat sore. Assalamualaikum warahmatullahi wabarakatuh.
Selamat sore. Terima kasih banyak, Pak.
Terima kasih banyak, Pak.
Don't forget to fill the presents and fill the berita acara. Thank you.